this computer. Okay, hello guys, and today we will be again quickly going through the one-dimensional search methods that we introduced last time. And if you have any questions, please interrupt me and ask me, okay? So I have named the chapter, this lecture, lecture 3 supplementary, because the previous lecture we actually began with it and you already have the lecture notes. So this is just something additional to that, just to make it maybe more presentable for some of our friends, okay? Okay. Okay, so basically, to begin with, let's define unimodal function, and I'm sure you all know what it is by now. So a unimodal function, let me activate my pen. A unimodal function is a function in which you have either one peak or you have only one value. So as you see in this function, this is a unimodal function because it has only one value, okay? But this guy over here is not a unimodal function. It is a multimodal function because you have multiple values, two values, 1, 2. Okay, so so the question that I was asked through an email by one of our friends is that what is the difference between the methods like bisection method and the graphical methods that we saw earlier and over here? In the graphical methods, I did not explicitly say anything about whether the function should be unimodal or not. Okay, if you remember carefully, I said that you have some interval, and in that some interval, okay, you try to find an optimal point, okay, a critical point. Now, if you have, for example, a multivariate function as shown, I'm sorry, a multimodal function as shown over here. And if I choose my points to be A and B, then by using any of those methods, I could either end up in this interval or I could end up in this interval. So the optimal point that it returns would be different. Okay, it could be either of these two. But what we do is now we assume that our function is unimodal, that I'm telling you that, okay, I'll give you a function and there's only one optimal point in this function. So what you want to do is you want to find a good interval or interval of uncertainty, or reduce the interval of uncertainty to some good intervals, so that then when you apply the graphical methods that we talked about earlier, we would definitely go to one of the we all would go to the same optimal point. Okay, so basically what we in the graphical method, the bracketing and open method, there is no assumption of whether the function should be unimodal or not. Okay, but over here in the this is also known as one-dimensional search. So in the one-dimensional search methods, I'm telling you that the function is unimodal, and you can use this to actually find an interval in which you can find the optimal point using any of the graphical methods. So is this clear? So in the one-dimensional search, I'm telling you that we assume that this function is unimodal, okay? Which was not the case in the graphical methods that we saw in the previous lecture. Okay, so quickly, just to recap, so a function is said to be unimodal if there's only one valley or there's one peak. So there's just one point. Okay, and obviously it is a function which maps a real number to real number. And what we have is a unconstrained optimization problem, which we want to find the minimum. We want to find some x value which returns the minimum f of x value. Okay, so we want to find the point x star which has the minimum f of x value. And we assume that this particular point, optimal point, would be denoted by x star. Okay, so the x star is the optimal point in a unimodal function within a given interval. And also, I told you the definition of the unimodal function. This is another summarized definition. The other definition is given in the lecture notes. But over here, we can say that a function is said to be unimodal in such a given interval if there exists 2 points x1 and x2 such that x1 is less than x2 within this interval, and these two conditions hold. Okay, so we talked about these conditions. I will not spend much time on this. So if these conditions hold within a given interval for 2 points x1 and x2, where x1 should always be less than x2, then we say that that function is a unimodal function. Okay. Okay. Now, so what we are doing is we want to find a good interval in order to search for the optimal solution in a unimodal function. And that's when we use a one-dimensional search method, or all these methods that we have studied and we will be studying today, okay? So the first method that we saw was the unrestricted search method, if you all remember. So I guess you guys remember. So the first approach was unrestricted, and there were two versions of this. The first version was using the fixed step size, and the other one we having an adaptive or accelerated step size. So for the fixed step size, do you have any questions? Does everyone understand how does the unrestricted search method using fixed step size work? Yes or no?
Yes.
Yes.
Okay,
Yes.
Asad, then can you explain to us, please?
Uh, I guess it will be difficult for me
Why?
because I need to recap the lecture after the lecture each time.
You have to recap the lecture after the lecture. So are you
Yes,
promising me
yes.
that you're studying?
Yes, sure. You can see my assignment in my quiz.
Well, I look forward to that because I haven't actually, that is done by your TA, but I will definitely look at your quiz. Hey, Baris, can you please explain to me?
Yes, so with the fixed step size, you check every interval, some interval delta.
Okay.
So whenever, if we're looking for minimum point, so after every step size, if the function decreasing, so this means that we are approaching the minimum point.
Okay. So you promised me you're studying, Baris?
Yes.
Okay, please. I mean, the only way that I can confirm is asking you to promise me. Okay, I really like to trust everyone. I really don't want to create a bad impression of any one of you. So please, guys, study. If you have any questions, email me or ask me. Do not feel shy. There's no reason for you guys to feel shy. This is an unprecedented situation. If it was a classroom, probably it would have been much more easier. But I do not want you guys to feel shy. Okay, ask me if you do not understand, if you do not want, like me also, please do a Google search. There are lots of resources out there. Look into them and make sure you understand it very clearly. Okay, because tomorrow you'll be getting your next assignment, and it will be a programming assignment based on this. So make sure you understand it very carefully. All right. So let me quickly just go through this. So we had so one approach is the unrestricted search, which is a fixed step size. And this is a very naive approach, or probably the first approach that would come to our mind. So what it says is that we begin, I mean, we'll have some fixed step size. In this lecture, in these slides, I've denoted that by delta S, okay, which is step. And we have a starting point x1. So for example, if you look at this function, this is my function, okay? And what I want to do is I want to find an interval, okay? I have not given you an interval and I'm saying, okay, apply, I don't know, bisection method and find the optimal solution. So you say, oh, okay, but we need a bracket, okay? What is my interval? I didn't give you any interval. So you say, okay, I will use, for example, one of the one-dimensional search methods, say unrestricted search with fixed step size. So what you do is you start with some initial point. So you take a point, arbitrary point x1, evaluate it at that point, so you get f of x1. Okay, and you set some step size. Normally, you set the step size to be small. If you use a big step size, normally what happens is you may get a bigger interval, and then afterwards, when you apply bisection, you will have to do more number of iterations. But if you use a small step size, you probably will have to, do the what we say more number of functional evaluations. But in the end, you will get an interval which will be much smaller and which will get you to the optimal point much faster. It will converge faster if you use any of the graphical methods. Okay, so you have to choose delta S wisely. So if you start with x1, then what you do is you add delta. So you find the next point, which is x2, which is x1 plus delta S. So you move and you find the next point x2. Evaluate them at f of x1 and f of x2. Okay, so we have 2 points and we have to compare them. Now, if the functional value of f of x2 is lesser than or equal to f of x1, then what you do is go to step 4. And what is step 4? Step 4 says, okay, do another find another point, x3, which is again x2 plus delta s. So keep in mind that you move in that direction, okay? So this point is something that you have to keep in mind. At some point, you may need to even change your direction. So I keep going that, I'll keep doing this as long as this condition holds, okay? And you find x3, and that's the point over here. Now what you do is you again calculate x3, compare it with x2, and if x3 is greater, I mean the functional value of x3 is greater than x2, then you do something else. But over here it's not the case, so you keep doing that. And so since x3 was f of x3 is again lesser than f of x2, what you do is I need to clear this for you so that you guys see. So what you do is you just relabel them, and now your x1 becomes your x2 becomes your new x1, and x3 becomes your new x2, and again you repeat this step 2. Okay, so you evaluate them and you keep doing that. You find a new point which becomes x3, and since over here x3 is again lesser than this point, so you basically say, okay, so this minimum point is somewhere between here, and you get your interval. Okay, so you keep doing this until and unless this condition is satisfied. So is it clear, everyone? So this approach gives you an interval. It gives you an interval which guarantees that, okay, now your optimal point, in this case minimum point, is within this interval. Then you can use any of the graphical methods that like bracketing methods, because you need a bracket to actually find that point. Okay, so you keep doing this until this condition is satisfied. Okay. Again, depending on the value of delta S, you can get a bigger interval, a larger interval, or even a smaller interval. So that's why it depends on your function and delta S, what interval size you get, okay? So there's a trade-off between choosing the size of delta S and having more number of iterations in your bracketing method. Okay, if no questions, we can move on. Can I move on?
Yes.
Okay. Now let's see, okay, the other version was, okay, using instead of a fixed step size, let's make it adaptive, or let's make it something that changes with time. So if we know that we are going very slow towards, our progress in reducing the interval of uncertainty is very slow, why don't we take a bigger leap or make a bigger jump, okay? So instead of having a fixed size, what we do is, and this was the example which was in my notes and I repeated over here, what we do is we accelerate the step size. So instead of using gamma to be 1 every time, what we do is every time we increase gamma. So if in the first step, if I take delta S to be gamma to be 1, that means delta S is equal to delta S, and I know that this condition is satisfied, so I need to find a new point. What I do is now instead of taking delta S, I take a twice delta S, which takes me to x3. Okay, and so in this case, with two iterations or two comparisons of step 3, I actually find an interval which satisfies this condition over here, and therefore I can quickly actually find this interval or this bracket in which I have to search for the optimal point. Okay, so by accelerating delta S, you can actually the step size, you can actually do it much faster. Okay, so this is just a slight improvement to the previous case. Okay, so unrestricted search means, the reason why it's called unrestricted search, because I'm not restricting you to search within a given interval. I'm not giving you any interval x of S and x of F. Okay, so there's a function. This is your function, and find the interval yourself. So that's why it's known as unrestricted. Okay. Okay, so assuming that there are no questions because no one is interrupting me, I will move on to the next guy. So we talked about this. So the next one is the exhaustive search. And we even talked about this. So let me find someone who's going to explain this to us. Maksat Anwar Bek, could you please explain this to us, sir? What is exhaustive search?
Yes, in exhaustive search, we divide the interval to a fixed number. Am I correct? Or no?
You tell me, I don't know. You're teaching me. You teach me.
We check by 3 points, as I remember. And by evaluating function at these points, we make some conclusions.
Okay, let's see what Yarasel has to add. Yarasel, do you think our friend is right?
Well, I would say partially.
Okay, could you make it completely right?
Yes, so for this method, we need to know the limits of this function. So our interval should be finite, and we need to divide it to the equal parts, n parts. And yes, and we can evaluate it like part by part with length.
Okay, so tell me, what is the advantage and disadvantage of like, how do I choose my my n value? The n is the number of points that you have to put within the interval in order to partition it into equal sizes. So what happens if I take n to be some large number? Say we have this interval xs and xf, okay? And say I can choose n to be 5, or I can choose n to be 50. What happens if I choose n to be equal to 5? What is the good thing and bad thing about it? Yarasel.
So maybe if we choose like great value of n.
No, n is equal to 5. Okay. Suppose I give you some points. Say, let's say our interval is from 0 to 10. Okay, and I tell you n is equal to 5. That means you have to place 5 points in between 0 and 10 such that it divides the 0 and 10 into equal parts. So 10 divided by 5 would be 2. So the size of each interval would be 2 units, right? Now, if I take, and so n is some small value, n is 5. So what is a good thing and bad thing about this? Remember that we have a function, and calculating the functional value, evaluating the function at each point is actually, it takes some, it's expensive. It takes it requires some cost, okay? So if n is equal to 5, it means that I have to do just 5 evaluations, right?
Yes, on the 5 iteration, and it will be faster, but the accuracy will be low, maybe.
Oh, very good. Yes. So the accuracy or the interval that it will return would not be as accurate. Accurate in terms, that means when you have to apply some what is that? Graphical methods, it will take more number of iterations over there, right? Because your interval will be larger. Am I right?
Yes.
Okay. So if n is equal to, now if I take it to be 50, that means I divide between 0 to 10. And I place 50 points in between, right? So that means the size of each interval would be 0. Yarasel.
0.2, what?
So 10 divided by 50, what is it?
Yes, 0.2.
0.2? Right?
Yes.
Yes, so the size of each interval will be 0.2. Now I have smaller intervals, but now I have to evaluate the points 50 times, right? I have 50 points to evaluate. So I have to do more than previous, so 50 means I'm doing 10 times more. But in the end, the interval that would be returned would be much smaller, right? And then when you apply any of the bracketing methods, it will quickly converge and give you the answer. Am I right?
Yes, you're right.
Good. So is everyone following? Did everyone understand? So choosing n over here again is tricky, something up to you. And depending, so if you have to implement it, don't ask me what should n be if I haven't given you. Just choose some number, say I've chosen it to be this. Or you can, to impress me, what you could do is you can do it for multiple n's, for small n, large n, and you show me, okay, see, if I use small n, this is what happens. These are the number of iterations it requires in the bracketing method. If I use a larger value of n, this is the number of iterations it requires. So you do a comparison, and that would like say, okay, I say, okay, this guy knows what he's doing. All right. Okay, good. So now let's get back over here. So basically what we do in exhaustive. Yes, sir.
I had a question. Is there a big difference between the fixed unrestricted search and the exhaustive search? Like in both cases, we have a fixed amount of region that we
difference. One difference between the unrestricted and exhaustive. In unrestricted, I do not give you an interval XS and XF. Okay, you have to start with single point. So if you look over here, all I give you is a starting single point. That's what I try to emphasize on. Okay, so if you are given just a point and you're given some step size, that is how you begin. So you find an interval in unrestricted. But in exhaustive, you are given an interval. Where's exhaustive? In exhaustive, I give you an interval. I say that, okay, there is an interval, okay, from 0 to, for example, 11 over here, okay? So in this case, example, oh, this is overlapping. 1 minute, sorry. Where is it? Exhaustive. So this guy. Okay, sorry about that. Shift 5. Okay, so in exhaustive, what I tell you is I give you an interval. Okay, so I say, okay, there is some interval of uncertainty, and you have to try to minimize this interval, okay, to some reasonable or good interval by using exhaustive search. So first thing, you have an interval. Second thing is you have the number, or you have to know what n value is in advance. So I tell you that divide it into, I don't know, 5 parts. So if I tell you to divide it into 5 equal parts, that means you need 4 points in between XS and XF, right? Because n points will give you n plus 1 parts, okay? That's what I talked about last time. Is that clear?
Yes, clear.
Okay, another thing that you have to do is the other difference is that in unrestricted, the number of functional evaluation, okay, depends on when this condition is satisfied. Okay, so you do not know in advance how many functional evaluations you have to do, right? As long as this is not satisfied, you keep doing it. So once it's satisfied, you stop. But over here in advance, in exhaustive, you know in advance how many functional evaluations you have to do, because you have endpoints. So you have to evaluate them at these numbers. So you'll have n number of functional evaluations. Am I right?
Yes.
So there are slight differences. So that so again, if you have n is very large, so you'll have to do many functional evaluations. If n is small, you have to do less. But on the other side, in unrestricted, we do not know what this n values, how many evaluations are required. We know that at least 3 evaluations are required, because we know that we have to find at least 3 points which would satisfy this. But at most, no one knows. Depends on the shape of your function. Okay.
Yes.
Good. Did I answer your question? Is it clear?
Yes, it's clear now.
Good.
Thank you.
Okay, so over here in exhaustive, just to emphasize again, we are given some interval, but this is a very, I would say, a very rough interval, okay? And we know that the function is unimodal within this interval. What we want to do is we want to try to reduce the size of the interval in order to converge faster to the optimal point using a bracketing method or any of the methods we saw earlier. And also, I should know in advance how many points or how many parts you want this interval to be equally divided into. So we have to know this n. So let's define some L naught as the length of this interval of uncertainty. Okay. So I think, why is my paper? See, okay, I did this on my computer at home, but when I bring it here, it overlaps. Okay, so L naught is actually, so if this is my given interval from XS to XF, L naught is the length of the initial interval of uncertainty. Okay, so the initial interval, this is the length which I denote by L naught. So L naught means in the very beginning. Okay. Where are we? Okay, so obviously L naught, the length of that interval would be XF minus XS. Okay. So what we want to do is we want to keep reducing this length. So we want to reduce L naught as much as we can until this condition is satisfied. That means until we find 3 points which satisfy this what is elimination condition. Okay. So what we do is, okay, so we have this and we have n. Do the following. First, we calculate how many parts we need. What should be the size of each of those parts, because they should be equal. So if A, B over here basically means X, I should write it as XS and XF. So this is xf and b is xs. So xf minus xs divided by n will give you the size of each interval, each smaller part. And there I can place these points. So I need exactly, if I want n, so I can place each of these endpoints at where xs, okay, plus delta x, which is the size. And then x2 would be x1 plus delta x. And we keep doing this until the very end. Okay, so I can place all x endpoints between these between the given interval xs and xf, okay? And then what I do is, again, another thing, as I told you, is in exhaustive search, you have to evaluate the function at all of these endpoints, okay? So for all i's from 1 to n, you have to evaluate fxi, okay? So we know that we have n number of function evaluations. But in the previous method, unrestricted, we do not know that. We know that at least 3 evaluations are needed, but at most, no one knows. But here we know that at most, n number of evaluations are needed. And then we take 3 points at a time and we evaluate until, so we move sequentially from here and we take 3 points as long as this condition is not satisfied. Once this is satisfied, we just return the interval. So if, for example, it is satisfied between these 3 points, we return the interval. So basically we have to return 2 intervals, right? So if this is I, this would be I minus 1 and I plus 1, right? If this condition not satisfied, that means this function doesn't have a unimodel, doesn't have a minimum point, you can say that there exists no minimum. So this basically, this doesn't have a unimodel. This is not a unimodel function, okay? So you keep doing this until this is satisfied. So basically what is returned is at least 2 intervals. Okay, so this is 1 interval, this is 1 interval, this is second interval. So at least 2 intervals because we're evaluating at 3 points. Okay, so the length of the final interval that would be returned would be the xi plus 1 minus xi minus 1. So 2 intervals. So 2 out of the n plus 1 intervals times the total length. So this would be the length of your final interval. Is it clear? Anyone, everyone?
Yes.
Does anyone have any questions? For those students, I don't want to take names, but those students who asked me to prepare this and to revise, are you following? Well, obviously you won't answer because then everyone will know who you are. But if anyone is not following, please just stop me, okay? Okay, so this is an example I want you guys to work out and pay attention that over here, we have taken x of s where x of s are not included, but over here I've taken 0 and 5 where 0 and 5 are included. So I've given you some interval of uncertainties, including a 0 and 5, and I asked you to take n to be is equal to 10 for this given function. So I want you to think about how, it's not a big thing to think about, but it's not like 0, 5, excluding 0, 5, okay? It's including 0, 5. So how would you slightly modify our algorithm to actually accommodate these 2 points as well? Any answer? Sultan.
Well, maybe just in the step 3, we have to account for it. We should start checking from 0, not the second point. Maybe.
Okay, so basically you'll have to just do 2 more evaluations, right? You have to include 0 and 5, right?
Yes, I think.
Yes.
Yes.
So it's a very simple modification. Nothing. Nothing very difficult. What I wanted to tell you over. You have to pay very close attention and careful with what is asked in the questions. Okay. My questions are maybe sometimes I require you guys to be creative and think. But sometimes my questions are so easy, and I'm so confident that students believe that it's so easy that they start working, but they don't pay attention to the question. So pay attention to the question. I've asked you to include 0 and 5. Other than that, everything else is just straightforward. Okay, good. So let's move. Okay, let me fix this guy. Probably I'll just do this. You go up and you go up. I guess that fixes it. Okay. Now, dichotomous search, okay? Dichotomy, does anyone know what it means? It's an English word. Does anyone know what it means?
Is it something for binary?
No, what's the English? It's an English term, dichotomy. So what is the meaning, the literal meaning of this word? Why is it used in this search? Why is it such a fancy name? Why does it have such a fancy name? Dichotomy, you can do a Google search right now and tell me.
Basically, it means antonyms, maybe.
Contrast.
Dichotomy means?
Antonyms.
Contrast.
Right.
Contrast, difference. Am I right? Dichotomy means difference, contrast, something that is different. That means I appreciated the dichotomy between these two opinions. That means the difference between these two opinions. Or we should respect the dichotomy between our friends or between the opinions of our friends. So dichotomy means difference. And basically what we're doing over here is again finding the difference, and I'll tell you why. Okay, let's look at the motivation behind why dichotomy is better than the exhaustive search that we just saw. Obviously, exhaustive search, one drawback is that if n is very large, you'll have to evaluate it at n points, whether we like it or not. Okay, so that's a lot of evaluation. So how about if we just locate our next point or evaluate our next point depending on the current evaluation, the evaluation of the current point, okay? So we do not have to do it n times, but we do it only depending on the evaluation value of the current point, okay? So basically what it does is, in other words, the dichotomous search, and obviously if we take x, and we are given an interval xs and xf, so the length of the interval of uncertainty initially would be L0, as shown over here. Obviously, what it does is, in simple words, it tries to divide or reduce or eliminate the interval of uncertainty by almost half in every iteration. Okay, and when I say almost half, it's not exactly half. It depends on, again, how small or how big the value epsilon is chosen to be. Okay, so okay, since we have already discussed this earlier, let me see if I can find someone. Igrim, could you please explain to us what is dichotomous search? We studied this last time.
Well, actually, I don't remember.
Come on, Igrim. Why not? Are you studying?
Yes, but I'm, as I said, recapping.
You're like Asset.
Yes.
So make sure next time before you come, wake up early, you revise, because next time I will ask Asset and you again, okay? So please make sure you study before you join the lecture. Everyone.
Yes. Okay.
Let's see. Daniar. Daniar Musa.
Yes. Yes.
Could you explain to us, sir?
In the dichotomous search, as its name says, like we should contrast two parts. First, we should find the length and then divide it into two parts. It doesn't matter to be exactly the same part, because in each time, like we have different values of here epsilon, and then in this middle point, x0, we just choose 2 points, x1 and x2, with the distance of epsilon over 2 between x1 and x0, and the x0 to x2. And then we should just substitute these values into the function, like x1 and x2, and so eliminate like in each iteration we should eliminate from this distance, like from xs to x1, and then from x2 to xf.
Okay, I believe you know how it is, how it works. So yes, I guess you know it. So I'm confident now that at least you understood it. But let me quickly just go through it, and so I just make sure everyone else also understands it. Okay, thank you. So the first step is, given an interval, a very initial interval of uncertainty, which the length is L naught. What we do is first divide it exactly into half. So we take the xf minus xs divided by 2. Okay, so we find the midpoint, which we denote by x naught. Okay, so x naught is the midpoint of this interval. Now, for some epsilon value, and we assume that epsilon should be some small value, we do not take it to be big, and I'll tell you why. Epsilon is some small value. So to the left and right of x naught, we take some epsilon divided by 2 distance, and we identify 2 points, x1 and x2. So basically, in dichotomous search, in every iteration, what we do is we evaluate twice, right? So we find 2 points every time, and we evaluate the function at these 2 points, x1 and x2. Okay, so x1 is x naught minus epsilon 2, and x2 is x naught plus epsilon by 2. Okay, so you evaluate the functions at x1 and x2, and then we use the elimination rule. And the elimination rule is that if if you look at my notes, there were 3 cases that the elimination rule says that if the function of what is that? X2 is functional value of X2 is greater than the functional value of X1. What you do is you keep this guy, and we know that the unimodel, the optimal point will not be anywhere beyond X2. So what we can do is we can eliminate this part. So what we keep in that case would be this length. So we would have a length of L naught half, right? Plus this point. So we'll have L naught half plus epsilon half, so which you can write as L naught plus epsilon half. Or if otherwise, then we choose the other half, not half, the other part, and we can, eliminate this part. Okay. So depending on using the elimination rule that we have seen earlier, every iteration we try to reduce the length of this interval by almost or nearly half. But it's when I say nearly, it's because it depends on the value of epsilon. Okay, and we keep doing this until that condition is satisfied, or the distance between x1, or the interval between x1 and x2 is like smaller. So we can say that, okay, absolute value of x1 minus x2 is less than some, I don't know, let's call it not epsilon, let's say E. Okay, so E is some point, you can say E to be 0.001. So if the distance between these two is very, very small, then we are sure that we have approximately reached our optimal point, and that's when you can stop. Or if the elimination rule satisfies, then that you can stop and use any of the other graphical methods to actually find the optimal point. Okay, so with that said, now one thing that I needed to I needed to tell you, because I asked you guys to find the value, the general form L of n. For L of n, how we would get that equation. Do you remember that, guys? I had asked you to, for example, this is Fibonacci. For interval halving, yeah, so dichotomous. I'd asked you guys to work out and see how we can find this. Do you remember? Everyone?
Yes.
Okay, so in order to find this, I probably I just want to give you some more information, because that's straightforward. But the things that you need in order to find the general form is you have to try to relate the number of iterations you have in this dichotomous search. Okay, how many iterations, and the number of function evaluations. So to do that, I have denoted M to be the number of iteration. What is iteration? That means in the first iteration, you have this, and after finding the midpoint, you apply minimum elimination rule, and then you reduce it, and again, you repeat this, find 2 points. So every time you repeat it, so in every iteration, you're actually evaluating 2 new points, okay? So you have, in the first iteration, 0 evaluations. Before you start, initially, you have 0 iterations. In the first iteration, you have 2 evaluations, because you find 2 points. In the second iteration, again, you find 2 points in the reduced interval, and so forth. So n, which is the number of function evaluations or experiments, as I mentioned earlier, is always even, right? Because it will always be 2 4, 6, 8 in every iteration. So in one iteration, it would be 2. In the next iteration, it would be 4. In the next iteration, you add 2 more, which will be 6, and so forth. So what I want to do is, if you can relate m with n, okay, then it would be easy to find this equation. So for dichotomous search, I have actually done it for you because I was not sure whether you guys would be able to do it. So I have done it for you. So keep in mind that in each iteration, you have 2 function evaluations, so 2 experiments. So n will always be even. Is it clear? Do you all agree with me?
Yes.
Okay. So in the very beginning, so when we have L naught, we haven't started anything yet. So at the start, when so there will be no iteration. So m is equal to 0, and we have no function evaluations in the very beginning. So we are just given xs and xf. We do not evaluate any of the points, and we haven't started yet. So m is 0 and n is equal to 0. So the length of the interval would be L0. Then when we take the first iteration, that means when we want to find the first 2 points, that means x1 and x2. So n would be 2 because we have to find the functional value at these 2 points, x1 and x2, right? This is step 3. And we have to do the functional evaluation at these 2 points. So we have n is equal to 2. And the new length, L2, which is this guy, would be either this or this, right? It doesn't matter. So it will be L naught plus epsilon divided by 2. So L2. So n is equal to 2. And since n is even, so we also use the subscript of the value of n. N is equal to 2 means we have 2 points at which we have to find the functional value. And the length we have already seen reduces to L naught plus epsilon divided by 2. So L2 would be this. Now, if we take it to the next iteration where m is equal to 2, so we have already done 2 iterations. We have to do 2 more iterations. So 2 plus 2 will give me 4. So L4 would be this plus epsilon divided by 2. And instead of L2, I can replace it with the initial L naught because that's what we know. And L naught plus epsilon 3 divided by 4. Okay. So if you keep doing this, and that is the reason for this dot, dot, dot. So in general, if I have some arbitrary m iteration, n would be equal to 2 times m, right? So if you look, every time n is equal to the relation between n and m is this guy. So at the end, so for n, L to the subscript 2m, which is basically this is same as n, ln would be equal to, but if I want to write it in terms of m, it would be L0 plus 2 to the power m minus 1, because 3, 1, so it is some odd value here, the coefficient, divided by 2 to the power n. So if I write it in terms of n, all I have to do is replace m with n half, right? Because take this 2 on the other side, m is equal to n half, and you would get this. So basically, this is what was required in the notes that I showed you earlier, and we proved it. So is this clear? I hope you guys have used the same approach. Any questions? Good.
I have a
No.
question.
You have a question?
Yes.
Yes, sir.
I was just wondering why don't we use number of iterations? Why we have to use number of experiments? Because anyways, we know that it's
because
2 times m.
I could have asked you a question. Okay, based on the number of iterations, prove or find me what would be the final length of the interval. Or I could ask you, based on the number of functional evaluations, tell me what would be the length. So depending on what I ask you, you would have a different value. So you would either give me this or this, right? So I just wanted to, I mean, I'm giving you information so that a food for thought. So in the exam, if you see either one, you know exactly how they are related. Did I give too much information? Shouldn't have I given this to you?
I was just wondering because we can't have partial iterations. In every iteration, we perform exact number of experiments.
Yes.
So why don't we stick with iterations?
You can stick to any one, depends on what I ask you. So you should be able to interpret the final length in terms of the number of iterations, because as you said, in every iteration, we know that we have a fixed number of evaluations, which is always 2. And since we know that we have a fixed number of iterations, which is always 2, so for n number of evaluations, which so obviously n would be a power of 2, and therefore, so it will, I'm sorry, product of 2, And therefore, so depending on what I ask you or what is important, you could do this or this. It doesn't matter. Both are the same. And the reason why for dichotomous search probably is easy, but once we go further and we do it for the other search, you see that relation is not that easy. Because not always, it's not always true that in every iteration we have even number of evaluations, okay? So probably over there you have to find a different relation, and the final length would also be different depending on what variable you account for. Okay?
Fine. Yes, thank you.
You're welcome. Okay, so one thing that I want to tell you, and I didn't explain in that lecture, handwritten lecture, is about a reduction ratio. So what is reduction ratio? Reduction ratio is the ratio or the amount of how much of the interval is reduced upon every 2 successive iterations. So from one iteration to another iteration, how much of the interval am I reducing? Okay, so that is known as, reduction ratio, or RR for short. So if I go from iteration 1 to iteration 2, iteration 1 means from the starting to the first iteration. So the reduction ratio would be L0 divided by L2, right? If you substitute L2 to be this, you would get this. Now, I could further simplify this, or this could be a reduction ratio. And if I assume that this epsilon is very, very small compared to L0, okay? So if epsilon is very, very small compared to L0, okay? And what I can say is that we can ignore this, and this L0 would cancel off with this L0. So I would say the reduction ratio is 2. Am I right?
But this will be only in case of the condition.
Exactly, good. That's why I asked you, am I right? If you would have said yes, I would, and someone said yes, but I'm not right. This is only for these 2 cases, for the simple case. So what happens if it is for general? Okay, that would be an exercise. So what if I just tell you, okay, for, I don't know, L, so 2, so this is 2, right? So let's say 2i, okay, and L 2 I plus 1. So what would be the ratio of these two for general? Well, obviously I goes from, it can be 0 to n. So find me in general, what will be the reduction ratio? And again, it should be in terms of epsilon, and then evaluate or you analyze epsilon, and assuming that epsilon is very, very smaller than L0, okay, the actual size, then how would it matter? I want you to do it, and in the next class, I will ask Asset and what was our friend's name? I forgot. What was Igrim? Both of you, you should come up with this answer, okay? Yes, Igrim. Good. Okay, so this is about reduction ratio. So reduction ratio means that every 2 consecutive, any 2 consecutive iterations, how much of, how smaller or how reduced does our interval get? Okay, good. Now, interval halving. Well, unlike the previous dichotomous search, which reduces the interval by almost half, because of that naughty epsilon factor. Over here, this guy says, okay, let's get rid of that because I don't want to be, I don't want to depend on some epsilon guy. What I do is every time I will exactly divide it into half, okay? But over here, to do that, what we have is we have to have a different initial setting. So the different initial setting is that in dichotomous search, what was the initial setting? What were given to you? So initially you were given just an interval, which was XF and XF. I'm sorry, XS and XF, right? And then every time you divide it into half and you find epsilon and blah, blah, blah. But over here, what we do is we are given again the same interval, but what we do is instead of having two function evaluations and we're finding 2 points, x1 and x2, as we saw earlier, over here we have to find 3 points, okay? So what we do is we have this interval. I think I have a graph. Oh, good, beautiful. So we have this interval S and XF, which is L0. what we do is we divide it into 4 equal parts. That means I have to have 3 points which are equally distant from each other. So obviously, if you have 4 points, so x0 will always be the middle of the actual interval xs and xf. So I divide xs and xf into half x0, and I divide in xs to x0 into half x1, and x0 to xf into half, which will give me x2. So basically, I need now 3 points instead of 2 points. Okay. When I say I needed 3 points, means I have to evaluate the function at 3 points. Previously, also we needed 3 points. We needed the midpoint, but we did not evaluate the function at the midpoint. Okay. So basically, that's it. So we have 3 cases that you have to consider. And so first step, divide L0 into 4 equal parts. That means I need 3 points, label them as x1, x0, and x2, where x0 is the midpoint, and x1 is less than x0, and x2 is greater than x0. Evaluate the function at these points, and then there are 3 cases that you have to check. Okay, so what are the 3 cases? Case 1. Case 1 says that if f of x2, okay, this guy, has a functional value greater than that of f of x0, okay, and f of x0 is also greater than f of x1. Let's see if this is true. So this guy is greater than this guy is also greater than this. So this is case A, yes. So what do? It says that if this is the case, we can guarantee that the point, the optimal point, will not be in this interval. And it is true. You see it's somewhere over here. So we can just remove this, and we're removing exactly half. There is no epsilon here, so exactly from x0 to xf is just discarded. Okay, so this is case 1. Similarly, if you have the function on the other side and we do the same thing, we can say that we can discard the first half. Okay. And what happens if it is in between? I mean, the midpoint, I'm sorry, the optimal point is between x1 and x2, okay? So in this case, which is case C, what you do is you can discard this 1/4 and this 1/4, which together is also exactly half, okay? So in every iteration, for every case, we see that it eliminates exactly half of the interval, which is good. Now let's do this what is that called? Let's try to find the general form for L of n. So in the end, what would be the length of the final interval? So again, at the beginning, initially, when nothing happens, when there is no, when we do not choose any points, we are just given an interval xs and xf. M is equal to 0, number of iterations, and n is also equal to 0. So we have initial length L0. When m is equal to 1, the first iteration, this is for, I think, Sultan, who asked the question, why do we need m and n? Over here, you see now in the first iteration, we do not have even number. We have, so in the first iteration, another interesting point. In interval halving, only in the first iteration, we need 3 points to evaluate. After that, every time, we only have to find 2 new points. Because when I discard this guy, I already know the middle of this. All I need to find is half here. I mean, half of this and half of this. So every time I just evaluate at 2 points. Only in the very first iteration, I have to evaluate at 3 points. Is it clear, Sultan?
Well, I understand what you are saying, but look, we could make this equation more elegant.
Please tell me. Yes, sure.
L0 divided by 2 power of m. So isn't it simpler?
It is, but what if I ask you, okay, explain this in terms of the number of functional evaluations?
Number of experiments?
Yes, sir.
Well, then we can go to this. Just express m in terms of n.
And how would you do that? So you have to come up with this guy, right? You have to be able to come up with this guy.
But I still can understand why we have to complicate it. Yes, you can.
It's not complicated. It's very simple. I mean, this answer is right, okay? But this answer is right as long as I ask you to, for example, I ask you to represent the final interval in terms of the number of iterations. But remember that at each iteration, the number of evaluations may not be the same. Over here in the first, we had 3 evaluations, but the second one, we just have 2. Okay, now what if I ask you to represent this in terms of number of evaluations? So you have to definitely come up with this relationship. If you do not know this, you give me this, I said, well, this is a number of iterations, not evaluations.
Okay.
Okay, so if you compare this with dichotomous search, you see that there is a +1 factor. And the reason for +1 is if anyone understands this clearly, they should be able to actually, work it out and say, okay, in the first iteration, we have 3, but in every iteration that follows, we do not have, 3 again. That means it doesn't become what we say positive, negative, even odd, okay? It's always odd. Because every time you add 2 more function evaluations to find these 2 points. So 3 + 2 will give you 5. So in the next step, again, it will be 5 + 2, which is 7. And therefore, if I've written this down, I know this is simple, but I've just done it for the sake of presentation, okay? So that students know how I am going from step to step to get to this final general form. And so when you have n number of evaluations, so if I say, okay, write it in terms of n evaluations, then you should be able to write this guy and not this guy, because this is not in terms of evaluations, but this is in terms of iterations, okay? So that's why this coming up with this thing is important, okay? So for every method that we'll be seeing, this actually, what we say, varies. It's not the same.
Yes.
Good.
I see. Thank you.
Okay, reduction ratio again. So if you want to calculate the reduction ratio, so unlike the previous case where this epsilon guy was giving us a hard time, here there's no epsilon guy, and we know for any two iterations, successive iteration, you just take the ratio, it will always be equal to 2. Am I right? Yes or no? Guys. Alemjan, am I right?
Yes.
Yes, Professor.
Okay. Good. Let's see. Oh, that's where I finished. Okay. Oh, we are almost dead. Okay, so did you guys study Fibonacci search? Let me go back to my own. So, Fibonacci. Should I ask someone, or would you like to answer yourself? Baurjan.
I didn't get to the Fibonacci yet.
Okay, Marat.
Not yet also.
Why not?
Because it was not for quiz.
Good answer. Temirlan.
I also didn't study because we stopped here.
Okay.
And I thought you
So
would
unless and until I don't study, no one studies, huh? Okay, it's okay. We are not lagging behind. We still have time. So for next week, I will prepare this, and hopefully we'll complete this and we'll move on to our next chapters. So please, for next week, at least try to study it. And tomorrow you will have your next assignment, which will be programming, and the instructions will be given to you. Okay, so we'll stop here and we will continue on, Tuesday. Okay, if any questions at any time, do not refrain from emailing me. Please ask me, email me. If it's necessary, we could even have a Zoom, one-to-one Zoom, and I can explain it to my best capability, okay? But I need to make sure everyone is interacting, everyone is active, and everyone is really interested in learning this, and taking this course.
Okay.
Okay, thank you very much. And that's it for today. See you guys on Tuesday. Stay safe. Bye-bye.
Thank you.